Hi guys, good morning. Can you hear me?
Good morning, sir.
Morning,
Yes, sir.
sir. Yes, sir.
Yeah, I'm sharing my screen, so let me know if you can see or not. Oh, can you see my screen now?
Yes,
Yes,
sir.
sir. Please do.
Yes, sir.
Okay, all right. So we can start now. So in the last lecture, we defined vector space, and then in today's class, we will start by looking at some examples of vector space, and then we will introduce some more terminology on vector space. So what is a vector space? So let us recall what is a vector space. So suppose that so this is what we were learning, vector space. So suppose that we have a non-empty set V, okay, and then we have a field F. So this is a non-empty set, and this is the field. Okay, then and suppose we have two operation. One we called as plus. This is the operation from V cross V to V, and the other operation is the scalar multiplication, which we denoted by this notation. It is a function from F cross V to V. Now then, under these operation, this V is called a vector space over F if these two operations satisfy certain properties. That means first for addition, this is called vector addition. So it is commutative, associative, then existence of additive identity, existence of additive inverse. So if these four properties are satisfied for this addition, and then there are other four properties for the scalar multiplication. If these properties are satisfied, then V is called vector space under under these two operations. And to denote a vector space, we use this notation V over F and these two operations. When these two operations are clear, I mean they are obvious by looking at the definition of the vector space, then we can just write V over F to denote the vector space. Sometimes we also don't write the field, we just use V as a vector space when the field is well defined and it's norm. Okay, so let us start today's lecture by introducing some examples of vector space. So let us start with very basic examples. So let's start with so you tell me some examples of vector space. Can you give me some obvious examples, the examples which come to your mind first?
R over R, P over R,
C over
Yeah,
C,
just
P
one by
over.
one. Let me write one by one. So R over R. This is what you said.
C
So
over
R
R,
C over
C over R,
C over R is a vector space. What else? C over R under the additions and scalar multiplication define on C. What else?
C over C,
C
C
over
over
C.
C. Okay.
Rn over
Rn.
over R.
So Rn over R. Just to fix the notation, for this I will simply write Rn. So whenever I write Rn, it means it is a Rn over R. Okay. And what it is? It is it is a is a is a collection of all n tuples of the form x1 to xn, where these xi's belong to R for each I equal to 1 to n. Now How is the addition defined here? What are the two operations?
Component wise addition
Component
and
wise addition.
Component
scalar
wise
multiplication.
addition and component wise scalar multiplication. All right. So these details you can verify. So if suppose I ask you to check whether this is a vector space or not, then what you have to do, you have to. So far we have not learned anything else, so we only know the definition. So you will just go through all the properties. First you will check whether the two operations are well defined. Once they are, once you are convinced that they are well defined, then you check that the properties which are satisfied by the addition and scalar multiplication. Anyway, so what else?
Q over Q.
C over
Q.
C over Q,
R over Q.
R over Q. So in general, can you just by looking at these examples here, these examples, can you say something like in general that okay, this would always be a vector space?
Every field form a vector space over its subfield.
Yes. So every field forms a vector space over its subfield. So that's true. So therefore, in general, you can say that any field you take, any field over its subfield. Fine. What else? Give some more examples. These are the trivial ones. Can you give some more? Yeah.
Sir, space of M cross N matrices.
N cross M
Matrices.
matrices. Space of N cross M matrices over what?
Over field, any field like R.
What are these matrices? Like the entries of the matrices are coming from where?
Sir, the
Real
same
numbers.
Sir, R
field
M
on
cross
which we are
N.
taking.
Real numbers आएंगे sir.
Yeah, one by one. So let me write. Tell me what it is. So you are saying space of matrices, but you have to tell me what are the entries of this
Sir, we can take the entries from the field.
field. Okay. So you are saying that suppose that we have a field F, and suppose we have N cross M. Let me denote this notation. So I'm fixing this notation. So whenever I write this N cross M over F, that means it's a space of N cross M matrices. So where the entries are coming from the field F. So what are these? These are the set of all matrices of size N cross M, where these Aij's belong to the field F for all I in 1 to N and J in 1 to M. Okay. So this set, you can check that this set forms a vector space over F under usual addition and scalar multiplication of matrices. All right. What else?
Real symmetric and skew symmetric
Sir,
matrices.
polynomial up to degree n over R.
So let us write the first one. So he said some said that space of all symmetric matrices. Right? What do you mean by symmetric matrix? What do you mean by symmetric?
When it's transposed, it equals
A
to
transpose
itself.
equal A equals to A transpose.
Okay, so you are saying that space of, so I can write in the same example, you can verify that you are saying space of symmetric matrices. Okay. Now, is it over the same field? I mean, what are the, so you have to define this now. what field you
Re-
should take?
Real.
Space of symmetric matrices. So field is R. So you are saying that all real symmetric matrices over R. So that is the vector space. Fine. Now
Symmetric.
skew symmetric matrices over R. That is also
Hermitian over complex. Skew Hermitian.
Hermitian over complex. Skew Hermitian over. So
Complex.
you are saying Hermitian over complex. Is it true?
Entries from complex number.
So okay, so let me write these. So you are saying space of, so this is over R. This is skew symmetric matrices. This is also you are saying over R. Then you are saying Hermitian matrices. So when you are saying Hermitian, what do you mean by that?
A theta is equal to.
So you mean that, so let me write this way. So you are saying, and
Conjugate of A transpose.
okay, so let me write this. So the entries are coming from C.
Yes.
So then this is like, let's say, collection of all matrices of size n cross n such that a star we will denote it by star. So complex conjugate transpose A star is equal to A. This is what you are saying. Okay. So is it a vector space?
No, sir. It's over C not. It's over R, sir.
Yeah. So this set is not a vector space. Why
No,
this is?
sir, with entries complex number.
Yeah. So entries are complex number here.
Over R.
So this is over R forms a vector space, but not over C.
Yes.
Okay. So not a vector space. Why not a vector space over C?
Scalar multiplication is not.
It is not closed under scalar multiplication.
सर
Yes.
हर्मिशियन मैट्रिक्स का फील्ड्स रियल हो जाए तो सिमेट्रिक मैट्रिक्स
No, no. So here you, by with this notation, what do I mean by that? It's a n cross m matrices over F. But what does it mean? It means that the entries of the matrices are coming from the field F. Now when you say, so this is now the set, so you can call it, let's say, V. Now for this, you want this V to be a vector space, then you have to define some, you have to look at this over some vector or some field. Now this field you have to say that which field it is. So for example, now you look at this Hermitian here, set of all Hermitian matrices, n cross n Hermitian matrices. Here the entries are coming from, the entries of the matrix are coming from the field C, but then let me call this as, let's say, V. Now I want to check whether V is a vector space over C or not. Now if I want to say that this is a vector space over C, what I need to check, I have to first look at two operations. So usually when we talk about, if we are not particularly saying for some specific operations, then we can assume that they are the usual addition and scalar multiplication over of matrices. So here, when you are saying this is a vector space over C, you have to define the addition, and then you have to define the scalar multiplication. So this scalar multiplication is a map from F cross C to, oh sorry, F cross V to V. Now this F you have to say which field it is. Now when you are saying that it's a vector, when you are checking it's a vector space over C, then this F would be C. Now you can check that this is not a well-defined thing here. This is when you take alpha, let's say it's a complex number where the imaginary part is non-zero. So let's say alpha, you can take any, let's say 2i, and then whenever you do this, if you take any a in V, which is Hermitian. If you look at this alpha A, then this alpha A is not Hermitian because it is minus 2ia, and therefore this scalar multiplication, this set is not closed under scalar multiplication. If you want to check whether V is a vector space over C or not, but the same thing is true over R, because then in this case this is closed under scalar multiplication. This set is closed under scalar multiplication over R, and then you can check the other properties also, and therefore this forms a vector space over R. Is it okay?
Yes, sir.
Okay. Similarly, you can there are many other examples. There are standard examples. So let me write one or two more so that I can use these notations for in the following lectures. So like you have talked about Rn, we can also define Cn over C. So Cn, this Cn I will use for this vector space Cn over C, and what it is collection of all these Z tuples, n tuple, where this Zi is coming from C for all I. Okay, so this is a vector space over C. Similarly, you can also talk about Cn over R. So this is also a vector space. Cn over Q. This is also a vector space.
Q over Q.
Q over Q is also a vector space. Yeah, so there are many examples you can construct and you can verify. These are some standard. So we have already talked about these Euclidean spaces. We have talked about the space of matrices. Then what comes next? Space of polynomials. Some of you said space of polynomials. So yeah, tell me what it is.
Pn over R.
What is Pn?
Polynomial of degree n less than or equal to n.
Less than equal to n. Okay. So let's say again we have a field F. Okay. Then look at the set of all polynomials, which I denoted by this notation P over F. So what it is the set of all polynomials. So how would I define this polynomial if I want to write it mathematically? How would I write this set? Can some of you?
A0
A
A0
naught plus A1x
A1A.
plus
Right.
A2x square added
Right.
as An x to the power n.
Yes. A0 plus A1x, so on up to An xn. The AIs are coming from F for each I, and n belongs to set of all natural numbers. So it is the collection of all polynomials over F. So if let me write this as Px, all polynomials over this, right? Now,
Yes.
how would you define two operations here?
Point.
Yeah, what?
Component wise additions.
Yeah, you will add the coefficient, right?
Yes.
And similarly, you can define the scalar multiplication, and under these two operations, this forms a vector space. Okay, so these things you can verify yourself. Okay, so let us look at some. So these are some standard examples. Let me write one more. Space of functions. So we have seen space of matrices. We have seen space of polynomials. So next is space of functions. Again, the same way. Suppose that we have a field F. This is our field. And suppose that we have a subset S of F. Let's say non-empty. Okay. This is a non-empty subset of F. Then consider this set, let's say F, script F, of all functions from S to F. Okay, where f is a function. Okay, so this is the collection of all functions from this set S to F. Now we want to make this as a vector space, so we need two operations. So can you suggest two operations for this set?
Composition of function.
Composition of function. Okay, and how would you, so, and tell me the other one also, and then you verify whether it is a
Scalar multiplication. Alpha.
Pointwise.
so. Do you guys agree whether this f, this would be a vector space over these two operations?
Sir, a scalar multiplication might not be.
No, so he is saying two operations. One is the composition, and the other one is scalar multiplication.
सर composition नहीं होगा
Composition.
addition होगा
एडिशन होगा
addition ही
So
होगा
first you tell
यूजुअल
me.
एडिशन है स्केलर मल्टीप्लिकेशन
Yeah, and so let me finish. So you are saying that the under composition it won't be. But then you have to give an argument why it won't be.
Sir, composition may not be commutative.
Yes, so it may not be commutative. Therefore, you can verify this, that under the composition and scalar multiplication, this doesn't form a vector space because the composition is not commutative in general. So then you want to change this operation. So you want to replace composition by addition. So how would you define addition of two functions?
Sir, element wise
Element wise. What do you mean by element wise?
means a
F1.
plus g. Sir, a plus a. Addition of two function will be always with respect to each and every element. A plus
Yeah.
g,
So you
a
are
plus.
okay. So let plus and addition be defined as. So how would you define the addition? So if you have f and g2 functions, then their addition you want to define this way, right?
Yes, sir.
And scalar multiplication you want to define this way. And alpha belongs to the. So these two operations are well defined. These are usual addition and scalar multiplication of functions. And then you can verify that set F
ओके
under addition and scalar multiplication forms a vector space. Please mute yourself. If you are not asking anything, then keep yourself muted. All right, so these are some examples we have seen, but then there are many other examples you can construct yourself. You can also look at any standard book and textbook. You can find many other examples. You can construct your examples also, and you will see many other examples in the problem sheet. So let us move forward. We start with, let's say, by stating some simple results. So these are very simple results. Yeah, please mute yourself. Okay. So we have defined the vector space. We have also looked at some examples of vector space. Now let us look at some simple results. So these are very obvious things, but I want you to realize that although they look very easy, we use them very frequently, but some of you might not be aware of these things. So let us start by saying that a vector space. So v dot s dot means vector space. So a vector space has a unique additive identity. So possibly all of us are using this, but now we want to claim that this is actually the case. So let us prove this. Yeah. So tell me the proof. for this. You want to say that if V is a vector space, then it cannot have two additive identities. It will have only unique additive identity. So how would you prove this?
So by contradiction.
By contradiction.
Okay, so how would you do that?
Sir, we can also use both are equal
Yeah,
if
so
they are having two.
yeah, so tell me which way you. So if you want to use something,
We,
you are doing that this way, then you have to justify.
we
सर
let
दो
two
आइडेंटिटी करके उन्हें
then equal. We prove that two are equal. Both are equal.
So you are saying that, let's say 0. So suppose 0 and 0 dash. So these are just notation for additive identity I'm using. Suppose 0 and 0 dash are two identity, two additive identities. Okay. Then what? Then you want to show that 0 is equal to 0 dash.
So 0 plus 0 dash is equals to 0, and 0 dash plus 0 equals to 0 dash, and that's why 0 is equal to 0 dash.
Right. So 0, since it's a 0 element, and 0 dash also belong to the vector space. So by using the property that 0 is a 0 is an additive identity, this 0 is equal to 0 plus 0 dash. But then 0 dash is also an additive identity, and this 0 belongs to the vector space. The same thing can be used for 0 dash also. So this is equal to 0 dash, and that's all. So similarly, you can prove that every element in a vector space has a unique additive inverse. So how would you prove this? So here, just a minute, let me finish this. So every element in a vector space has a unique additive element. So whatever you say, it should be valid for every element. Okay. So now you tell me how would you start this proof?
let beta 1 beta 2 are two inverse of alpha.
What is alpha?
Alpha beta belongs to vector space.
So this is any alpha?
Alpha
Yes,
is
sir.
non-zero, sir.
Non-zero vectors.
So let's say non-zero then.
Alpha plus beta equals to identity element. Alpha plus beta 2 equals to identity element. By comparing, we will say beta 1 beta equal to beta 1 equal to beta 2.
Yeah, I understand what you are saying. So every element in a vector space has a unique additive inverse. So whatever you are saying, this should be true for every element. So then you say that, okay, let us suppose let V be any element. Suppose V is an element, and suppose that there exists U and W, two additive inverse of V. So let U and W be two additive inverses, okay, of this vector V. What does it mean? So this means that, so this abbreviation is used for that is, that means that means or that is, this notation. So that means V plus U equal to 0, 0 is the additive identity, and similarly you can say V plus W is equal to 0, because U and W both are additive inverses. Now you want to show that U is equal to W, so you know that U is equal to U plus 0, but then 0, you know what it is U plus V plus W. So you have used the fact that V plus W is an inverse of V, additive inverse of V. Now what is the next property we'll use here?
Associative with
Associative.
U plus W.
Yes. Then what?
V plus U equals to 0.
W.
U plus V equals 0 होता है
Yes.
inverse
Yeah, so this u plus v is same as v plus u because of the commutativity, and then v plus u we know this is 0, but then use the fact that 0 is an identity, so it is equal to
W.
So you see that we have used most many of the properties of a vector space. Here the property of the additive inverse, oh sorry, additive identity here. Then here we have used the additive inverse. Then here we have used the associativity. Then we have used the commutativity, and then again the additive identity. See? So this so we are, without realizing, in many cases without realizing, we are using some of the facts, but actually because of this reasoning we are able to use them. Okay, so since what we have seen here, that every element has a unique additive inverse, so we can call this additive inverse as, let's say, minus v. So this is just a notation. Minus v is just a notation. Okay, so this I will just write here. So since additive inverse is unique for every element, we can let minus v. So this is just a notation. Minus v is just a notation. So we can let minus v denote the additive inverse of v in. Okay, so this is just a notation. Whenever I write now minus v, that means it's a additive inverse of v. Okay, so let's prove the next easy simple property. If I multiply the 0 element of the field to any vector v, then it gives me the 0 of the vector space, 0 or the additive identity of the vector space. So this is true for all v in v. Okay, so what I'm saying, this is the 0 of field, or you can say additive identity of the field, and this is 0 of the vector space. That means additive identity of vector space. Now how do you prove this thing?
0 plus 0 equal to 0. Pre-multiply 0 into 0 equal to.
So what you're saying, 0?
0 plus 0 equals to 0.
So yeah, let me write this. So 0 plus 0 is equal to 0.
दोनों साइड v से मल्टीप्लाई करेंगे
So let's say this is what you want to say, right?
सर. राइट, यस सर.
So what is this 0? 0. So in the first line, this 0 is the 0 of field.
0 plus 0 डॉट, यस सर ठीक है. 0 plus
0 plus 0. So this is of the field.
यस सर.
Okay. So then this is what you are saying.
डिस्ट्रीब्यूशन ला लगाएंगे सर इसमें.
But why this step is not correct here? So can you tell me why this step is?
सर 0 is identity element.
The first step is fine. Second. So the problem here is that actually from, if you look at the right hand side, you are using the fact which you are trying to prove.
नो सर, इसमें अब डिस्ट्रीब्यूशन ला लगाएंगे ना तो इसमें कैंसिलेशन.
Yeah. So see, you are saying first look at this, and from here you multiply, so you get this one.
Yes sir.
So what you should start with is that from this step to this step, in proving the second step from first, you are, if you look at the right hand side, you are actually using the fact which you are trying to prove.
सर हम प्रूफ तो हमें 0 करना है ना, 0.
So this is
Sir,
the problem, whatever you are saying.
सर नेक्स्ट टाइम में अगर हम ये लिखेंगे 0.0 प्लस 0.0 इक्वल टू 0.0 तो लेफ्ट कैंसिलेशन ला से
Yeah, so
ये
I understand what you are saying, but the way you have started, that is not correct. That's what I'm saying. So if you look at 0 plus 0 equal to 0, and then when you multiply with a vector v, then in the right hand side you are actually using the fact which you are trying to prove. So what you should do is that you want to prove 0 dot v equal to 0. So you look at this. This is what you are saying, 0 dot v. Now this thing is equal to 0 plus 0 dot v. This is so far we have not used anything. This is what you were trying to say, right? Now you are saying you use the distributive law, so it is 0 dot v plus 0 dot v. Now everything is fine. We have so far used the things which we have learned. We are not using anything else. Now what?
सर इसका इनवर्स एग्जिस्ट करेगा एडिटिव इनवर्स तो ये कैंसिल हो जाएंगे आइडेंटिटी इसमें 0 ऐड करेंगे पहले क्योंकि आइडेंटिटी एलिमेंट है 0 प्लस 0.0 प्लस 0 इक्वल टू 0.0 प्लस 0 डॉट v.
Yeah, you look at my screen and then tell me what would be the next step.
So in the left hand side, we can write 0.v as 0.v plus 0 vector.
Well, 0 vector. Okay,
Then by left cancellation law, it will be equal to 0 vector.
what is left cancellation law? How do you know that this left cancellation law works here? We have not done this. What is how to prove this left cancellation law?
सर इनवर्स प्रूफ कर चुके हैं ना.
Yes, so you say that instead of saying that left cancellation law, you can say that you just add the additive inverse of 0 dot
Yes,
v,
sir.
both sides. This is what we know. We don't know what is left cancellation law. So what it is, so you just add, so adding the additive inverse of 0 dot v. This is a vector in v, in the vector space, so we can find its additive inverse to both sides. We get 0 dot v equal to 0. And that's all. Similarly, you can prove that instead of now if you multiply any scalar with the 0 vector of the vector space, then you get the 0 vector. This is also true for any alpha in F. The same way you can prove this also, exactly the same way. So this you can do yourself. You just write it alpha 0 as alpha dot 0 plus 0, then use the distributive property again, and then you can get it. Let me write one more property here. So when I multiply minus 1 is in F, the field. So minus 1 is the actually the negative of the unit element to a vector v, then I get minus v. Can you tell me how it is? How would you prove this?
Sir, by using third result.
By using
0 dot v is equal to 0.
Okay, then
Then write 0 as 1 minus
so
1
you are saying, let me write this 0 equal to 0 dot v, then
is equal to 1 minus 1.
1 minus 1. This is what you are saying. Okay, then
Then it will be equal
Distributive.
to,
so
Distribution law.
this you can write as, let me just write this, just a notation. I can write it this way, right?
yes sir.
Because this is in the field, and in the field we can do this. We want to use a similar property in the vector space also, but so far here I can use the property of the field, so I can write it in this way. Then I use the distributive law, would be this one. Then what?
एडिटिव इनवर्स लगाएंगे
Now
इसमें.
additive
इसमें
inverse
पहले
both
से
sides.
V plus
ये भी लिखेंगे
Now what?
Additive inverse.
Both sides.
Additive in.
Adding inverse of v both
Inverse
sides.
V.
Yeah. So this implies that -1 dot v, this quantity is an additive inverse, of v. But we know that v has a unique additive inverse, and therefore this implies that this -1 dot v is actually the additive inverse. But additive inverse we are denoting by minus v, so this should be equal to minus v. Okay. All right. So these are some very basic properties for vector space. So let us start. Let me define subspace. What is a subspace? So what is a subspace? Can you tell me what is a subspace?
A subset of the vector space is called a vector subspace if it is itself a vector space.
If it itself a vector space over the same
Over
field.
the same operation.
Over the same field or the same
Operation.
operation.
Right. So if you want to define, then you will say that, let's say we have a vector space over F, and suppose that we have a subset of V. This is a subset. Okay. Then this W is a subspace of V if W itself is a vector space over F or the same field F using the same vector addition and scalar multiplication of V. Okay. So before I give you example, I want to prove one result, or I want to state this result. You can, this is a very simple result which you can prove yourself, and then using that result we will see some examples whether a given set is a subspace of a vector space or not. So
So W is non-empty.
sorry,
W is non-empty.
W is
Non-empty subset.
so we are just saying for subset, any subset. We are not mentioning anything here.
Okay, sir.
Okay. So W is a, so you remember we W is a subset, it's a subspace of V if W itself is a vector. So this is what we are using so far. Okay.
Yes, sir.
W itself is a vector space over A, then we say that this is okay. Now if it is empty, then it won't be, no? It won't. Anyway, so let's see some example and then we'll discuss that. So you can check, you have already learned this. If we have a subset W of a vector space V, then this W is a subspace if and only if it is closed under vector addition and it is also closed under scalar multiplication. So the proof of this is very straightforward. So if suppose we have a vector space V over F and we have a subset of V, okay, then and here I'll say non-empty. Okay. Now I want to find a necessary and sufficient condition. So now I will specifically write. So suppose that this is a non-empty subset. Otherwise it won't make any sense. So in the definition I don't have to write this, but here I can clearly say, because if it is empty then it won't be a subspace. Now here, if this is a non-empty subset of V, then W is a subspace of V if and only if these two conditions are satisfied. That means the first one is that this W is closed under vector addition. That means if you take any two vectors in or two elements in W, then this implies that U plus V is also there in W. Similarly, it is closed under scalar multiplication. That means if you take any scalar alpha, and if you take any vector, any element in W, then this implies that alpha u also belong to W. Now if this you are going to prove, now this is a if and only if result, so you have to prove both sides. So one side is very straightforward, right? So which one is straightforward?
When W is
W
subspace.
is subspace.
So the if direction is straightforward. That means if W is a subspace, then it has to be closed under addition by definition, and it also has to be closed under scalar multiplication. So this is by definition. So this is straightforward. What about the only if direction?
W is closed under addition and multiplication or scalar multiplication. Then we have to prove W is a vector space.
W is a vector space, right? Now clearly you don't, so in order to prove that this is a vector space, W is a vector space, you need to check these conditions, whether this addition and scalar multiplication satisfy these 8 conditions of a vector space or not. Now some of these conditions are very straightforward, you don't have to check them. For example, whether addition is commutative or not, you don't have to check. Because why you don't have to check?
Because W is a
It's
subset of a
identity.
vector space.
Yes.
Yes. So
Also associativity.
Elements of W belongs to V.
So element of W follows the rules of the vector
right,
space.
because this is V is a vector space, so this addition is commutative since in V, so it would also be commutative in W. Similarly, the associativity and many other properties of scalar multiplication, they follow immediately. You only need to check two things. Can you tell me what are these two things?
Identity or inverse.
Identity and inverse, additive identity and additive inverse for every element. But this you can verify using these two properties. So this I leave as an exercise because you have some idea. So I leave this as an exercise. You finish this problem. Okay. So you write it properly and convince yourself that these two conditions are enough to check whether W is a subspace or not. Okay, now this result gives us a way to check whether a given set is a subspace, because in order to check whether W is a subspace, we just will quickly see whether W is closed under scalar multiplication and closed under vector addition or not. If it is, then we say that W is a subspace. We don't have to worry about the other properties. Because of this result, they will follow. They will also follow. All right. Now you can see some examples. So let me quickly write some examples, and then you can, for other examples, you can look at the textbook, or you can construct your own examples. I have also given some problems in the tutorial sheet. So for example, these are some very basic thing. R is a subspace of C over R, right? Every vector space is a subspace of itself. Similarly, if you look at the set containing only the zero element of the vector space, then this is also a vector space. These are the two trivial subspaces. One is the zero space, that means a set containing only the zero vector, and the vector space itself. By definition, they are subspaces of the vector space, and they are called the trivial subspaces. And I'm giving you examples of some non-trivial subspaces. Similarly, you can see Rn is a subspace of Cn over R. Similarly, as you mentioned earlier, if you look at the set of all Hermitian matrices, set of all Hermitian matrices of size n cross n, then this is a subspace. This is a subspace of n cross n matrices over R. Okay, but this is not a subspace over C. Subspace of a space of matrices. Similarly, you already have the vector space V as a space of polynomials, all polynomials. Now, can you give me two subspaces of this vector space V?
Even polynomials.
Even and
Sorry?
odd polynomials.
Even and odd polynomials.
Odd polynomials.
Any other example?
So nth degree polynomial and 0 degree and n plus 1
I did
degree
not.
greater than n plus 1.
Degree?
Degree less than n.
Less than equal to n.
Less than equal to n. And
No, so you are
n
saying three things. Just a minute. You are saying degree equal to n, degree less than equal to n.
नहीं,
Degree
एक तो less than equal to n.
so that's the
एक
only, yeah.
एक zero polynomial and degree greater than 1 n.
Greater than n.
हाँ
Degree greater than n.
हाँ and zero polynomial union.
But so how many of you are convinced with him? How many
sir.
are?
No, sir.
Which
Zero
one?
is not wrong.
No, sir.
Less than equal to के लिए तो सही होगा सर, बाकी के लिए नहीं.
Yeah, less than equal to के लिए सही होगा. But what about the greater than n?
Zero
No, sir.
union greater than
Sir,
n is
greater
also
than n.
Zero
Yes,
union
sir.
greater than n.
Zero union.
greater than n degree polynomial.
Zero
नहीं,
union.
नहीं होगा.
सर आप write down कर लीजिए.
So you're saying, let me first write Pn. So this is the notation for the space of all polynomials of degree less than equal to n. So you're saying all polynomial Px. This Px belong to the set of all polynomials such that degree of Px is less than equal to n. So clearly this is a subspace. So I agree. So this is a subspace. Subspace of. Now what else did you say? So let's say the other set you said is S.
Zero
Where
polynomial and generated by n plus 1, n plus 2, n plus 3 degree.
Okay. So you're saying degree of Px is
Greater than
n
n. Yes. And union zero polynomial.
union zero polynomial.
Yes.
Generated by n plus 1, n plus 2 ऐसे वाला.
What do
हाँ
you
वो
mean?
इससे वही हो जाता है.
x n plus 1, x n plus 2.
Okay. Now, can you verify why this is a subspace? How would you prove that this is a subspace?
Yes, sir, we
Sir,
can.
हो
Just
जाएगा ना
check these two
properties.
conditions.
Yes.
If you want to say this is a subspace, just check these two conditions whether they are following or not. So
Yes,
let's
sir,
take they are following. Let's take two
Sir.
polynomials, and if they are degree greater than n, then their addition would also be of degree
greater than n.
greater than. And here, since you also have this zero polynomial, and therefore this forms a subspace.
Yes, sir.
Because for scalar multiplication there won't be any problem, only the addition you need to check. For the addition, this including zero, this makes a subspace, but if you exclude zero, it won't be a subspace.
Yes, sir.
Okay, fine. So
sir,
yeah,
sir, अगर हम एक पॉलिनोमियल लें x to the power n plus
Sir,
x,
we can reduce degrees, sir.
दूसरा पॉलिनोमियल लें माइनस x to the power n, अब इनका जो बनेगा वो x बनेगा, बट x तो इसमें बिलोंग नहीं करेगा.
so you are saying xn plus x, and you are
माइनस xn,
so you are
अब
saying
एडिशन तो नहीं बिलोंग करेगा ना.
right. So it won't be a subspace.
Sir,
Right?
generated by ले रहे हैं ना, generated by
No.
degree
So you
greater
look
than
at
n.
this set. So this set
Sir,
doesn't
x
satisfy this.
x की डिग्री कहाँ पे है n+1 से ग्रेटर देन जनरेटेड बाय ले रहे हैं ना a नॉट x n+1 plus a1 x
No, no.
n+2
So
plus
yeah.
a2
So
x n+2.
just a minute. Just a minute. So these two things are different here. So whatever set I have written as this doesn't make a subspace because of this thing here. Because you can see that both these elements belong to S because their degree is greater than n. But when you take their addition, it is X, and therefore it is not a it's not closed under addition, and therefore it is not a subspace. Is it okay? So this is not a subspace. This is not a subspace. But now what you are saying that the if all the elements of P are of this form, like
सर
x
पहले
and
भी यही
1,
बोला था
let's say P tilde x,
हाँ generated by x n+1 greater than b.
then it makes a subspace. Yeah. So just whatever set you want to check whether it's a subspace or not, you just verify these two properties are satisfied or not. So this set is not a subspace, and you can verify this one. Okay, so let's move ahead again. Let me define sum and direct sum. So suppose that we have a vector space V over F, and let U1, U2, these are M subspaces of V. So these are subspaces. We have a vector space and we have subspaces of V. Then the sum of U1 to UM, this is defined by U1 plus U2 and so on. This is denoted by this notation. You just take the sum of this U1 to UM. And how it is defined? It is the collection of all vectors of the form this U1 plus U2 and so on up to UM, small um, where these small ui belong to capital UI for each I. Okay. Now this is how we define the sum of subspaces. So every element in this sum will be of the form u small u1 plus small 2 u2 and so on up to un, where these vectors ui belong to the subspace capital UI. Okay. Second thing, so I'm just fixing some terminology here. This vector space V is called the direct sum. So the first one was just the sum. Now I'm defining direct sum. This is called the direct sum of u1 to um if each element, let's say V in the vector space V, can be written uniquely as a sum, let's say V equal to u1 plus to um for some ui belong to capital UI for all I. Okay, so this term here unique, this uniqueness is important here. This makes direct sum different than the sum. And for just to denote the direct sum, we use the following notation. So this is the notation for direct sum. So when V is the direct sum of the subspaces U1 to UM, then we write V as this one. So on up to UM. Okay. So here this notation is just for sum and this one is for the direct sum. So this is just the definition. Now you can verify that if you are given, let's say, m subspaces, and when you look at the sum of these m subspaces, then it also forms a subspace. So sum of subspaces is again a subspace of a vector space. This you can verify. So this I will write this as an exercise. You can quickly verify this thing. This is very straightforward.
Sir?
Yeah.
Sir, please explain the unique sum.
No. So here I'm just saying this is the definition. Whenever I say something about the direct sum, then I will talk about this uniqueness. So what I'm saying here, in the sum, I'll give one example where you will be convinced that these two things are different. In the first, I'm not talking about anything. I'm just saying that the sum is defined by this collection where each vector, each element in this sum is of this form where ui's belong to capital Ui. Now in the second definition, I'm saying that it is called a direct sum where every vector v in V, so V is called a direct sum of these subspaces u1 to um, when V can be written, every vector V can be written uniquely as a sum of this. This is just a definition. Okay. Now I will give you one example. So let me first write this and I'll give you one example where you will see that why the uniqueness is important to write here. So this you can verify that the sum of subspaces is again a subspace. Again a subspace of V. Okay, so let us first take, because you asked this, so let us take one example here. So let me take u1 as, let's say, xy0, where this is some simple example in R3. Okay, so our vector space is R3 and u1 is this one, and I will take u2 as, let's say, 0, 0, z. Okay, or this one, and then this is in R, and similarly, let's say u3, let's say 0, y, where y is in R. Now, can you tell whether these u1, u2, and u3 they are subspaces?
Yes, sir.
They are
Yes,
subspaces.
sir.
Yeah, so they are subspaces of R3. Now, can you see whether what would be the sum of u1, u2, and u3?
R3, sir.
R3.
Q, sir.
R3.
R cube.
R3, yeah, R cube. So you are saying that R3 is equal to u1 plus u2 plus u3. Now you see here, if you want to prove this thing that R3 is equal to this, what you have to show? You have to show both side inclusion, right? This and this. Then only you can see. Now the one side inclusion is very straightforward, that u1, u2, u3, they are subspaces of R3, and because of this exercise, their sum is also a subspace. So this side, the first inclusion is very straightforward. So u1 plus u2 plus u3 is a subset of R3. In order to show that R3 is also a subset of u1 plus u2 plus u3, what you have to do? You take any element in R3 and show that it is there in u1 plus u2 plus u3. So how would you do that? So if you take any element in R3, it would be of the form xyz. Now this element xyz, you have to write as an element of this sum u1 plus u2 plus u3. That means you have to write this as a sum of vectors in u1, u2, and u3. So how would you write this? You can write it as xy0 plus 0, 0, z plus 0, 0, 0. So clearly you can see that this xyz belong to this sum, and therefore R3 is equal to this. So R3 is a sum of u1, u2, and u3. Okay. Now can you tell me whether R3 is a direct sum of U1, U2, U3?
No, sir.
No, sir.
Why not?
Sir, take an example like 1, 1, 1.
Hmm.
So this can be written as. So can you please written?
Yeah. So you're saying take
Can
1,
you
1,
please write? So this can be written as 1, 1, 0 plus
1,
0, 0, 1
0, 0, 1
plus 0, 0, 0.
plus 0, 0, 0.
And this can also be written as
This can also be written as
1, 0, 0 plus
1,
0, 0, 0
0 plus
0, 0, 0 plus
0,
0, 1, 1
0 plus
0, 1, 1. So
0.
this is not unique.
Yeah.
पर
So
इसमें
here
100 तो किसी सब स्पेस में बिलोंग नहीं कर रहा ना फिर ये
first one U1 में.
जो लास्ट
So this belong to U1 na?
ओके सर ओके
Yes,
सर ठीक
sir.
यस सर
So you can see that this 111 can be written. So you can see here in this example it can be written in two different form of elements from the sum U1 plus U2 plus U3, and therefore this 111 you cannot say that every element in V or in R3 can be written as a unique, can be written uniquely as a sum of elements from this U1, U2 and U3, and therefore this is not a direct sum. Now here is an example where you can say that this U1, U2, U3 forms a sum of R3, but they do not form a direct sum. And you can take another example, like let's say simple example. Instead of U1, U2, U3, can you say this thing here?
Yes, sir. Yes, sir.
यस
Yes,
सर
sir.
But can you also say that R3 is equal to this one?
Yes, sir.
Yes, sir.
Yes, sir.
यस सर
So you can see that this is a direct sum, but this is not a direct sum. So here R3 is not equal to direct sum of U1, U2 and U3. Now is it clear what do I mean by the uniqueness here in the definition of direct sum?
Yes, sir.
यस सर
Okay. So now you can see here, if suppose you are not, so here you need to see whether, if I give you a vector space and if I give you let's say m subspaces, and I ask you to check whether it's a direct sum or not. If you want to prove that it is not a direct sum, then you will quickly find an element in the vector space, and you will show that it can be written in two different ways as a sum of vectors in U1, U2, U3. If you want to disprove, right? Now you suppose you want to prove that this is a vector space, then how would you do? So in this case, it is very easy. Like in the second example, it was easy to see the elements of R3, and therefore you can easily verify this. If suppose I give you m subspaces, and the space is also, let's say some, it's not that easy to see. It's some vector space, and I give you m subspaces, and I want to ask that whether it is a subspace, whether it's a direct sum or not, whether the vector space is the direct sum of these subspaces or not. Now, to disprove, as you have done, you will take one example and check, and you will find two representation, and that will solve the purpose. But in the other case, if suppose you want to prove that this is a direct sum, then using this definition would be difficult, because this definition says that every vector should be uniquely written as a sum of the vectors from the subspaces. So you have to check for every vector. There are, how many vectors are there? There are infinitely many. You cannot check for every vector. So you need a way to check whether a given vector space is a direct sum of its subspaces or not, of given subspaces or not. So for this, I will write this next result. This result gives us a way to check whether given vector space is a direct sum of the given subspaces. Okay, so let me write this result first. So suppose that we have a vector space over the field F, and suppose we have subspaces u1, u2, and so on up to um. Okay, so these are subspaces. Then V is the direct sum of u1, u2, and so on up to um if and only if these two conditions are satisfied. The first one is that V is the sum of u1, u2, and um, and the second condition is that
intersection.
Yes. What is it?
Intersection equal to identity.
Single identity.
Intersection equal to
Single
Identity.
Additive identity.
Additive
Of
identity.
Okay, fine. So what do you mean by the intersection of identity? Intersection of all?
intersection of all the subspaces.
Intersection of all the subspaces identity. So now, okay, so before I finish my second statement, let us look at the example I gave you. Can you tell me what is the intersection of this u1, u2, u3 here?
Identity होगा इसमें सर, इसलिए होगा नहीं वो.
Why, sir?
So that intersection won't work here, right?
Yes sir. क्योंकि v1 v2 का इंटरसेक्शन ही 0 हो रहा है तो फिर दोनों का इंटरसेक्शन भी 0 होगा v2 v3.
Yes. So here the intersection, you can see it has only the identity, additive identity, but still you have an example where you cannot say that it is a direct sum of these three. So that intersection won't work here.
Pairwise.
The intersection of any two subspaces.
Identity.
Intersection of
Any two subspaces.
I'm not saying this M is 2, no, here. We'll see whether for M is 2 it is the case or not, because at least for this example we cannot use the fact that 2 subspaces because there are 3. So that result will not be useful here. So what you are saying that intersection of 2, if suppose there are only 2 subspaces, but I'm not talking about 2. The statement, if you look at, I'm saying that u1 to these are the subspaces. Possibly for the 2
intersection of any two.
Intersection of any two is identity. Then now again for the same argument, I will give you the same example here. Look at the intersection of any two here.
Sir, intersection of u1 plus u2 up to un minus 1 and un.
Intersection of u1, u2.
Sir, intersection of u1 plus u2 up to un minus 1 and un.
So what it is?
Sir, empty. Sir, ये empty होना चाहिए.
Empty. It will never be empty. There would be a 0.
That means zero identity.
Always be there.
Sir, अगर u equal to u1 plus u2 plus dot dot um है and any two subspaces का intersection 0 है तो ये सब direct sum होगा.
Yeah, so that's what I'm saying. So you look at the same example, u1, u2, u3 here. This example, u1 intersection u2 is 0, u2 intersection u3 is 0, and u1 intersection u3 is also 0. And intersection of these three
U1
is
intersection U3 is not 0.
U1?
Sorry.
U1
U2
intersection
intersection U3 equal to
U2 intersection U3 is equal to?
Sir, U1 intersection U3 is not 0.
Why?
Sir, it will be 0 y 0.
Yes.
Would be
दोनों
no.
सेम एलिमेंट नहीं सर, इंटरसेक्शन 0 ही होगा क्योंकि इसमें U2 में 0 0 Z है और इसमें 0 y दोनों सेम है ना, Z y और Z, वो कंडीशन फेल हो जाएगी फिर इसमें.
So now you look at here. Here we have example where any two intersection of any two subspaces is 0. Intersection of all of them is also 0, but still it is not a direct sum. It is a sum, but not direct sum.
Sir, y axis is belonging to U1 and U3 both.
U1 and U3.
साथ में फिर y एक्सिस भी तो फिर 0 होना चाहिए ना उसके लिए U3 में.
Look at the subspaces first. Convince yourself that it cannot be. So now whatever argument you were saying using the intersection will not work here. At least I gave you example where whatever you're saying is not true.
Yes,
So
sir.
now,
Yes, sir.
yes. So now I'm giving
we
you a
can
condition which doesn't say anything about the intersection, but it gives you a way to check whether it is a subspace or not, whether it is a direct sum or not. So the first condition, it has to be a sum first, which it should be by definition. And the second condition, it says that the only way to write 0 element as a 0 of the vector space 0 as a sum of U1 and so on up to UM, where each UI belong to capital UI, is the only way to write this 0 as a sum U1 to UM, where UI belong to capital UI, is the only way is the following, is by taking all the UIs 0, by taking all the UIs equal to 0. Or you can say that the only way to write 0 is the trivial way. That means you just write 0 as 0 plus and so on up to 0 m times. Now this condition tells you that you only check for the 0 vector, whether the 0 vector is written uniquely or not. If it is written uniquely, then you say uniquely means obviously 0 can be written as 0 plus 0 plus 0. So if the only way to write 0 is the trivial way, then you say that V is the direct sum of these subspaces. Now this condition is very useful. This is very strong because it says that you only check for the 0 vector and that's all. You don't have to bother about the other vectors. So you can look at this example here. Although here you have checked for this non-zero vector. So to disprove this, it is fine. But to prove, you just check for the 0. So if you write 0 vector as a sum of these vectors in the subspaces UI, look at this. If you have two different representation for 0, then you say it is not direct sum. Otherwise, it's a direct sum. So let us prove this one. So this is a if and only if result. So we have to prove both ways. So just a minute. So first prove the if direction. So suppose that V is the direct sum of. So what is the if direction? Suppose V is the direct sum of these subspaces. Now we have to prove that these two conditions. The first condition is very straightforward, right? By definition. Do you agree with this? The condition A is straightforward, that V is the sum of.
Yes, sir.
This is by definition, because for the direct sum it has to be a sum. Not only that, every vector has to be uniquely written. So this is by definition. So this is the first condition is straightforward. Now for the second condition, we need to check that the only way to write 0 as a sum of vectors from the subspaces is the trivial way. So we have to prove this. So let's say we can write, let's say we write 0 as u1 plus so on up to um, where um belong to capital, oh sorry, ui belong to capital UI. Okay, and we also know that this 0 can be written as 0 plus 0. So if we show that these UIs are 0, then we are done. Then we can say that the only way to write 0 as a sum of these sum of elements from sum of vectors from these subspaces is the trivial way. Okay. Now from here, can you say that the only way to write 0 is the trivial way? So since we know that v is the direct sum, so by definition every vector has to have a unique representation as a sum of vectors from these subspaces. Now here, if we know that 0 always can always be written as a sum of zeros, so 0 plus 0 plus 0 and so on up to 0 plus 0 up to m times. And if we write 0 as u1 plus u1 plus u2 and so on up to um, then this gives us two way, but that is not possible because v is the direct sum. So this implies that each of these ui has to be 0. Since 0 is a vector in v, so this implies that by uniqueness, by the definition of the direct sum, this 0 has a unique representation as a sum of vectors from these ui's, and this implies that each of these ui has to be 0. So this proves the if direction. It's very straightforward. You don't have to write this, but by definition it follows here. The only if part is important here. So suppose that v is the sum of these ui's, and the only way to write 0 as a sum of vectors from these subspaces is the trivial way. Okay, using these two conditions, we have to prove that v is the direct sum of these ui's. Now how do you do that? Can you give me some idea?
सर बाय कॉन्ट्राडिक्शन एक v को लेंगे और उसको दो वे से रिप्रेजेंट करेंगे.
So let me write this. Okay, so let me write what you are saying. So you are saying that let us suppose there exists, you want to prove it by contradiction, so let us suppose there exists a vector v such that v has two representation. This is what you are saying, right? So let's say u1 u2 and up to um, and it can also be written as, let's say, v1 v2 and so on up to vm, where these ui and vi belong to capital ui for each I, right? This is what you were saying.
Yes sir.
Right.
सर
Now
ये आपस में भी इक्वल है.
आपस में भी इक्वल है, right?
यस सर. तो सर एक साइड जैसे ui राइट साइड है तो उसका इनवर्स हम दूसरी साइड अप्लाई करेंगे.
Okay.
तो वो सारे एक जगह आ जाएंगे. तो
So
क्या बनेगा?
let me write this. So you are
Yes.
saying that from here we can say, because both of these things are equal to v, so this sum is equal to this sum, and then you can apply the inverse of the elements from one side to other side. So you can write it as u1 minus v1 plus u2 minus v2 and so on up to um minus vm, right? This is what you were saying.
Yes, sir.
Then
The only way to represent 0 is 0. तो ये सब के सब 0 के इक्वल हो जाएंगे.
right. So the only way now, using the second thing, using the fact that only way to write 0 as a sum of the vectors from these subspaces is the trivial way. This implies that each of these ui minus vi has to be 0. So ui minus vi is 0 for each I, but this implies that ui is equal to vi and for all I, and therefore you can say that every vector has a unique representation when you write this as a sum of vectors. So this is a contradiction, and therefore you can say that v is a Fine. So now you have a way to check whether a given vector space is a direct sum of given subspaces or not. But then you said that initially before this result you said some result using the intersection. In fact, when you are given only two subspaces, then that argument will work, whatever you were saying. So if suppose V is a vector space and U and W are two subspaces of V, then V is the direct sum of U and W if and only if V is the sum of U and W, that means V is equal to U plus W, and the intersection of U and W contains only the zero element, zero vector. So this is true. So when we have only two subspaces, then this result will work. This result is true. But if we have more than two subspaces, this is not true, as we have already seen an example. Okay, so I will write this as a result, but then you can prove it yourself. I'll leave this result as an exercise. So suppose that we have a vector space V. So let V is a vector space. And suppose that we have two subspaces U and W of V. So these are subspaces. Okay. Then V is equal to U. V is the direct sum of U and W if and only if V is the sum of U and W and intersection of U and W contains only the zero vector. Okay. So you complete the proof, or you write the proof yourself. I give you this as an exercise. Okay. So this result is true. So whatever argument we were giving for this example, this result doesn't fail here, because that result is true for only for two subspaces, and here we are looking at this example for three subspaces. So we haven't missed anything here. All right. So okay. So let me next define linear combination. Okay, linear combination of vector. So since we have only 3 minutes, so maybe I will start this topic in the next class. You can work out these exercises. I have also uploaded a problem sheet based on this vector space, subspace, basis, and dimension. You work out these problems and you come up with your doubts in the discussion session today at 2 p.m. Okay, so we can stop here because we only got 2 minutes. So if you have any doubt, you can ask.
सर वो पॉलिनोमियल ऑफ डिग्री एन का लास्ट वाला समझा दीजिए।
क्या
सर वो पॉलिनोमियल ऑफ डिग्री एन जो लास्ट लिखा था x to the power n+1 सर वो
So you just check. You have a way to check, na? So what is the problem there? You have a way to check whether so what I was saying is that if suppose you have all polynomials, you have a set of polynomials where the polynomials are of this form, where this p tilde x, this is of the form a0 plus a1x and so on up to an xn. So what I'm saying is that each term in this polynomial is a polynomial of degree n+1. Exactly, I mean greater than equal to n+1. So this is the set of all such polynomials. For this set, you see whether this forms a subspace or not. So union 0.
Okay, sir.
Okay. This forms a subspace or not. So just take. Sorry.
सर फर्स्ट के 2 स्लाइड्स देखना थी, थोड़ा सा लेट हो गया था.
So I will upload this, so don't worry. These are just simple examples, simple vector
Yes.
space examples. Okay, I will upload this PDF as well as the recording. I will upload on Impartus. So in the last lecture, I had divided the recording into two parts. First part I have uploaded. The second part is I don't know why it's not being uploading. So I'll try again, and I'll also upload today's lecture.
Okay, thank you, sir.
Okay. Anything else?
Thank you, sir.
Sir,
Yeah.
sir, Pn wala example, sir, the example which you've taken for the polynomial of degree n plus 1 for
Mhm.
subspaces P tilde 1, sir. Sir, that is going to make subspace or not?
Yes.
It is going to make, sir.
No, no. So I'm saying, I'm asking you. So you just check these two conditions. You verify these two and tell me what is the problem, where is the problem, or if there is at all a problem.
Sir, means I wanted to ask that P tilde, when you are taking P tilde n, at that time you are taking all such collection which forms subspace up to degree n or something else. P tilde n representation
Yeah.
means.
So here you have to fix this n. You have to fix this n.
And sir, what
So
does P tilde n
here,
means?
when I'm talking about such a set, then you have that means you have to assume, because here you see P and X. This is what we were talking now. P and X is a polynomial of degree less than equal to n. So this n is
Yes.
fixed, and depending on this set, we were talking about this set here. So for a fixed n, you have to check this. Yeah. Is it okay now? Just verify these two things and tell me. So this is an exercise for you. You tell me, you give me some argument whether it is or it is not a subspace.
Okay, sir.
Okay. Anything else?
So,
Yeah.
sir, I have doubt in previous lectures, sir.
Yes, please go.
So regarding, so when two system of equations have same solution, then they are equivalent. How do we prove this?
How do you?
How we prove this, sir?
If they have same solution. Let me. This we have proved, no? We have we gave some example, if you remember. So which lecture it was? I guess this one. Yeah, those who want to leave, they can leave because the class is over now. Which lecture was it?
This thing I do not remember. Sir.
I think it's the third lecture.
Fourth lecture? This one. Not fourth lecture. This one. Yeah, so equivalent systems of equations have exactly the same solution. This is what you are asking?
Yes, sir. In this way, I can prove. Like in the reverse way, sir. When the systems have same solution, then
When
how
the
do we prove
systems
that they are equivalent?
when the systems have same solutions, So first of all, you need to see whether this is correct or not. This is true or not. So the converse of this. Suppose we have two systems, they have exactly the same solution, then whether they are equivalent or not. So let's see it in this way. Okay, so yeah, what about these two? So I was thinking about some counter example.
Sir,
Yeah.
sir, it is a proof. Sir,
So true. Okay.
yes, sir, it is a proof.
Let me just see this. We have, let's say, homogeneous system ax equal to 0 and bx equal to 0. These are two solutions. These are two systems. And suppose that ax equal to 0. And so x is a solution for a for the first system, then x is also a solution for b. And this is true for all x. Using this, we have to show that a and b are equivalent. Okay.